On the left is an air-filled parallel plate capacitor, and on the right is a capacitor that's been filled with some sort of insulating material that we describe as the dielectric material. Air is a dielectric whose dielectric constant, indicated here by the Greek letter kappa, that's not the letter K, that's a Greek kappa. The dielectric constant for air is equal to 1. The dielectric constant for anything other than air is greater than 1. The air-filled parallel plate capacitor has a capacitance we'll call C0, and it's equal to the permittivity of free space multiplied by the area of the plates and divided by the distance between the two plates. The capacitance of the capacitor on the right, assuming the plates have the same area and are separated by the same distance d, has a larger capacitance. C is greater than C0, and the capacitance is equal to epsilon times A over D. Just a slight difference, right? I didn't put the subscript 0 along with the epsilon. So this is the permittivity of free space, or the permittivity of air, where this is just referred to as permittivity. So how do we find what the value of the permittivity is? Very easy. The permittivity of the dielectric material is the dielectric constant multiplied by the permittivity of free space. So if we wanted to, we could say the capacitance is equal to kappa times epsilon naught times A over D. Well, how exactly does this work? Why does a dielectric make the capacitance go up? If we look at it on a somewhat molecular level, a lot of these dielectrics are made out of polar molecules. So instead of drawing the three-dimensional view of the capacitor, let me just simplify that and draw. There's my top plate, there's the bottom plate, and when it's connected to a source of potential difference, electrons are removed from the top plate, put on the bottom plate, and in the end it becomes charged up, electrostatic equilibrium is achieved, and there's a very nearly uniform electric field. Now we take our dielectric material, place it in here, and assume it's made of polar molecules. Now let's zoom in and draw these polar molecules. Figure not drawn to scale. There's a molecule, it's got a positive and a negative end. There's another polar molecule, it's got a positive and a negative end. There's another one with a positive and a negative, and they're all sort of randomly oriented in here. Actually, not really. That's how the molecules would be arranged if they weren't sitting in the space between the charged plates. What actually happens all those molecules align. There's a torque on an electric dipole. Hopefully you remember this from our very first unit of study for this class. When an electric dipole is placed in an external electric field, it receives a torque and it rotates. So all these polar molecules are going to rotate into an alignment like this. This is the positive plate of our capacitor. This is the negative plate of the capacitor. And so they're rotating, the molecules that is, so that that's the negative end, that's the positive, that's the negative, that's the positive, negative, positive, and so on. So we're going to be left with a layer of molecules on the bottom surface of this slab of dielectric, and there's going to be a overall positive surface charge along that dielectric. just because of all the positive ends of those molecules. And then the layer of polar molecules across the top surface is going to leave us with a negative surface charge density, right? And then there's all the molecules in between, etc., etc. So effectively, we have the positive capacitor plate and the negative capacitor plate, and the electric field associated with just the charge of those plates. But simultaneously, there's this dielectric slab that has a negative surface charge across the top and a positive surface charge across the bottom. So I'm going to describe the electric field here shown in red as being the electric field external to the dielectric material. In other words, the electric field just associated with the conducting plates of the capacitor. But then we end up with a weaker induced electric field, indicated here in pink, that's associated with the surface charges across the opposite ends of the dielectric material. So we end up with a net electric field that's equal to the external field, minus the induced field. In other words, the electric field has gone down in magnitude. Well, that seems strange that reducing the electric field would make the capacitance go up. The result of reducing the electric field is that the capacitance goes up. Well, the potential difference across the capacitor, delta V, is just equal to the strength of the electric field times the distance, right? These plates are separated by some distance d, and so if the electric field decreases, then the voltage across the plates decreases. So what we're imagining here is the plates were at one time connected to our battery, but then a switch is opened up once we reach electrostatic equilibrium. So whatever amount of positive charge was conducted onto, electrons were conducted off of the top plate. So it's as if positive charge was conducted to the top plate, negative charge was conducted onto the bottom plate, and so then we introduce this dielectric material. Nothing can change the amount of charge that's on these plates because our circuit is now opened up. And because the electric field got weaker, due to the fact that the electric field is now opposed by some induced field, the electric field got weaker, so the potential difference across the plates became less. Well, capacitance, as you know, is defined as the ratio of charge compared to voltage, but the charge stays the same when this dielectric slab is inserted and the voltage has gone down. And so what's the effect? Right, the capacitance increases. So this is a molecular description of why inserting dielectrics in between the plates of a capacitor increase its capacitance, and almost any capacitor that's produced commercially has material other than air in between the plates. It can be oil, it can be plastic, it can be some sort of wood fiber or pulp. It could be neoprene, it could be rubber, It could be, well, on and on. Most physics textbooks have a table somewhere in the chapter that we're studying here, this chapter on capacitors and capacitance, and in that table they'll list several materials, and next to it the value of kappa. Now kappa is a dimensionless quantity, meaning it carries no units. So the permittivity of the dielectric material is a dimensionless quantity multiplied by the permittivity of free space, and therefore the capacitance of a non-air-filled capacitor is equal to, well, if it's parallel plate anyway, instead of epsilon naught A over D, it's just epsilon A over D. Okay, that's the parallel plate capacitor. Now we also know the formula for the spherical capacitor. We say it's equal to, well, if it's all air in this space right here, it's 4 pi epsilon naught AB over B minus A, if A is the radius of the inner solid sphere and B is the distance to the inner surface of the outer spherical shell. That's if it's air-filled, but if it's filled with some material other than air, some dielectric material, then you guessed it, the capacitance is equal to 4 pi epsilon AB over B minus A. So the form of the equation doesn't change. The geometries still affect the capacitance in the same way. But because epsilon is always greater than epsilon naught, due to the fact that kappa is always greater than 1, it's very simple to solve for the capacitance of a non-air-filled capacitor. You just have to multiply by the dielectric constant. Simple as that.